Hey there, science fans! Today, we're diving into the fascinating world of finite element analysis, or FEA. It's like a digital crystal ball, letting engineers and scientists predict how things behave under stress, heat, and other forces. But here's the secret sauce: boundary conditions. Imagine trying to predict the weather without knowing where the wind is blowing or how hot the sun is. That's what it's like to run an FEA simulation without boundary conditions. They're the invisible forces that shape our simulations, telling us how the edges and surfaces of our objects interact with the world. Without boundary conditions, our simulations would be like soap bubbles, pretty to look at, but ultimately meaningless. Boundary conditions ground our models in reality, making sure they reflect the real-world constraints and interactions that determine how things behave. So buckle up as we explore the world of boundary conditions. The unsung heroes of FEA simulations will uncover their mathematical origins, explore their different types, and learn how to apply them effectively. Get ready to unlock the secrets of accurate and insightful simulations. Okay, science fans, let's get a little mathy for a moment, but don't worry, I promise to keep it painless. At its heart, FEA is all about solving equations, specifically partial differential equations. These equations describe how things change in space and time, like the temperature of your coffee cooling down or the stress on a bridge as cars drive over it. Now here's where boundary conditions come in. These equations need a starting point, a set of known values that tell them what's happening at the edges of our object or system. These known values are our boundary conditions. Think of it like this. Imagine you're baking a cake. The recipe with its ingredients and baking time is like our partial differential equation, but the recipe alone won't guarantee a perfect cake. You also need to know the size and shape of your pan, right? Those are like our boundary conditions, defining the limits of our cake and influencing how it bakes. So, boundary conditions are like the mathematical fences that enclose our simulations, ensuring our equations have the information they need to make accurate predictions. They're the mathematical anchors that keep our simulations grounded in reality. Okay, enough with the equations. Let's see how boundary conditions play out in the real world. Imagine a cantilever beam, like a diving board. One end is fixed, unable to move, while the other end is free to bounce up and down. The fixed end represents a displacement boundary condition. We know exactly how much it can move, which is 0. Now let's picture a chair. When you sit on it, the legs experience a force pushing down. This is a force boundary condition, telling us the external load acting on our chair. Without it, our simulation wouldn't know you were even there. How about a hot cup of coffee? The heat from the coffee flows into the surrounding air, cooling it down. This heat transfer is governed by a thermal boundary condition, defining the temperature difference between the coffee and the air. Ever wonder how car windshields are designed to withstand impacts? Engineers use FEA to simulate crashes, applying pressure boundary conditions to represent the force of impact. This helps them optimize the windshield's shape and materials for maximum safety. These are just a few examples of how boundary conditions help us simulate real-world scenarios. From bridges to coffee cups, boundary conditions are essential for understanding how objects behave under various conditions. Section 4. Types of boundary conditions, a diverse toolkit. Just like a handyman needs different tools for different jobs, engineers have a variety of boundary conditions at their disposal. Let's explore some of the most common types. Structural boundary conditions. These deal with how objects move and deform under force. We've already met displacement and force boundary conditions, but there are others, like constraints that limit rotation or specify how surfaces slide against each other. Thermal boundary conditions. These govern heat flow. We can specify temperatures, heat fluxes like the heat from a stovetop, or convection conditions like the cooling effect of wind. Fluid flow. Boundary conditions. These control the movement of fluids like air or water. We can define flow speeds, pressures, or even simulate free surfaces like the ocean. Electromagnetic boundary conditions. These are used in electronics design, antenna analysis, and more. We can specify electric potentials, magnetic fields, or wave impedances. Specialized boundary conditions. There are even more specialized boundary conditions for acoustics, chemical reactions, and other phenomena. The possibilities are endless. Section 5. Applying boundary conditions, best practices and pitfalls. Applying boundary conditions correctly is crucial for accurate simulations. Here are some best practices. Understand your problem. Before diving into software, clearly define the physical situation you're modeling. What are the known constraints and interactions? Choose the right boundary conditions. Select the boundary conditions that best represent the physical reality of your problem. Using the wrong type can lead to inaccurate results. Apply boundary conditions carefully. Ensure your boundary conditions are applied to the correct regions of your model. A small mistake can have a big impact on your results. Validate your results. Always check your simulation results against common sense and, if possible, experimental data. If something seems off, double-check your boundary conditions. Common pitfalls to avoid include over-constraining your model. Applying too many boundary conditions can make your model too rigid, preventing it from behaving realistically. Under-constraining your model. Not applying enough boundary conditions can lead to instability, causing your simulation to crash or produce nonsensical results, ignoring symmetry. If your problem has symmetry, exploit it. You can often simplify your model and reduce computational time by simulating only a portion of it. Section 6. The importance of accuracy: garbage in, garbage out. Remember, science fans, in the world of simulations, the old adage holds true: garbage in, garbage out. Inaccurate boundary conditions will lead to inaccurate results, no matter how sophisticated your software. Think of it like building a house. If your foundation is weak or uneven, it doesn't matter how beautiful your windows are or how sturdy your roof is. The whole structure is compromised. Similarly, inaccurate boundary conditions undermine the integrity of your simulations, making their predictions unreliable. That's why it's essential to approach boundary conditions with care and precision. Take the time to understand your problem, choose the right boundary conditions, apply them accurately, and validate your results. By doing so, you'll ensure that your simulations are built on a solid foundation, capable of providing meaningful insights and driving innovation. Section 7, Conclusion. Boundary conditions, the unsung heroes of simulations. So there you have it, science fans. Boundary conditions may be the unsung heroes of FEA simulations, but they play a vital role in unlocking the power of this incredible tool. They are the mathematical anchors that ground our models in reality, the invisible forces that shape our simulations and allow us to predict how things behave in the real world. By understanding the different types of boundary conditions, their mathematical origins, and the best practices for applying them, we can unlock the true potential of FEA. We can design safer cars, build more efficient airplanes, develop innovative medical devices, and push the boundaries of science and engineering. So the next time you see a simulation, take a moment to appreciate the invisible forces at work, the boundary conditions that make it all possible. Keep asking questions, keep exploring, and never underestimate the power of a well-placed boundary condition. Stay curious, my friends.